So we'll have a quiz today, but I plan on reviewing sorting because we really haven't done too much with that. And that's just simply because of the time. We'll have a quiz on sorting today after we review, but again, that'll be after we review. So the primary things that are going to be on the final exam that we haven't just, learned, right? It's like what else is there to learn in the last 2 weeks? Well, we have the sorting stuff, right? So you're going to need to know about some of the sorting stuff and then graphs. So my plan is that, I give you guys time to work as well as demo today. And then I'll put up the latest assignment. The assignment for this week is actually going to be a fairly light assignment. One that you should actually be able to fulfill, that if you do it in class on Wednesday, you should actually be able to get it all done. And it's simply it's a twofold process. It is that I want you guys to learn how to use external libraries because that's something that you may not get a lot of experience on. Okay, so then we'll work on a graph problem that's dressed up like a security problem for next week for our final assignment, and then I think we can start reviewing our assignments. Reviewing for the final exam. Hopefully on Wednesday next week. Definitely the last class on Monday will be dedicated towards review period. Right. I will be writing the final exam. However, it is a common final. It's also open book and open note. One thing that you should know though is that I haven't made a practice of making a practice final exam for this class. What I do instead is that I give you guys a link to a whole lot of other final exams that are at different universities and going through them and kind of being surprised at how much you guys know. Like for one thing, we'll look at one thing I'll enjoy doing is that we will be taking a look at some entrance exams for universities into the graduate computer science program and noticing that, hey, we know those data structure questions, we might not know what those automata questions or those math questions are because that's what they focused on. But hey, that we know the part that we actually, have learned about. All right. So we've learned a number. So there were a number of sorting algorithms that we have learned over this. And they might be a bit hard to keep straight, but here's what we've learned so far, right? So first and foremost, we have selection sort, which is dead. So I guess I'll just use I'll just use this because it's better than my handwriting anyway. Okay. Okay, so what sorting algorithms do we know? First and foremost, we have selection sort. Now, why do we care? Now, selection sort is one of those. I taught you guys 3 O of n squared algorithms. 3 algorithms that run in O of n squared time. The first was selection sort, which was terrible because no matter what, it's going to run in O of n squared time, right? Which makes it fairly terrible. The reason it runs that way is to review. Is that what it does? Is that we take the very first. We look for the smallest item, right? We look through all the items that are unsorted, take the smallest one and put it into the first spot. Then we look through the remaining items, take the next smallest item and put it into the second slot, and so on and so forth, right? So, right, if I bang on the keyboard here for a second. Right, and let's go ahead and look at that. Right, if this is our array over here that I want to sort with selection sort, how's that going to work? Well, I will look for I'll look through all these items, find the smallest item, and put it into the first spot. So I'll swap 8 and 1. right? Then look for the next smallest item. Look at all these items, find out 2 is the smallest, and then I'll swap 2 and 8. So it's a fairly simple algorithm, but the worst case scenario for it is that it actually does extremely poorly and I believe I went over this in the videos, if you give it something like this. Right? If you give it something like this and ask to sort it, right? Or more realistically, if I give it something like this, let's go ahead and search for the first item, search for the smallest item, and put okay, found it, and I swap it with itself. Then let's go for the next smallest item. Okay, found the next smallest item. I got to swap it with 2 and 3. Okay, now for these guys, I got to find the next smallest item, found 3, swap it with itself, find 4, swap it with itself. So we've already finished sorting this thing, but we got to continue with the whole algorithm anyway. You know, merge sort suffers from this as well as and actually Quicksort, this is pretty terrible, but it's not as terrible as what happens with selection sort, because selection sort is O of n squared. So why do I bother learning it? Well, because when I say it's an O of n squared algorithm, we are talking about the number of comparisons. So you have 2 ways of basically computing the cost of sorting stuff. The number of comparisons, in other words, how many times do I have to say which one is bigger, which one is smaller? And then there's the number of exchanges, which is the physically moving 2 things around. Right? This one we do a lot of comparisons, but we actually only do O of n exchanges. Now, moving things around in memory, very, very cheap, so we don't bother really about the cost. Comparisons, though, can be actually kind of expensive. However, if we're not actually performing this on a computer and we're actually sorting giant slabs of stone that literally weigh tons, then perhaps we really care about the number of exchanges we make versus the number of comparisons. Yes.
Would it matter if you're inserting into an array list? Is that the insertion itself?
Well, with swap, we'd swap. You would do in-place swaps for all these. An exchange is always a swap, so no need to reorder. Where that does come into play is merge sort, right? Next we had bubble sort, which is a bit better than selection sort. It's also very popular as your first sorting algorithm because it's got such a playful name, which is basically, let's look at these pairs of items and then swap them if they're out of order, and you just keep doing that until it's sorted. So that one I don't really feel a need to go into too much, except that, again, its worst case scenario is if it's in reversed. The final one I want to talk about, though, is the final O of n squared algorithm that I like talking about, though, is insertion sort, which is really actually useful, even though it's O of n squared. First off, as I may have mentioned on the videos, it's an online sorting algorithm, which is something that the other sorting algorithms don't have as a quality. Which means that basically, right, if I'm sorting like 100 items, and then my boss tells me, hey, you've got to sort 100 more items. Sorry, we forgot half the items. For all the other sorting algorithms, I pretty much have to start over, right? I have to start over from the beginning. Selection sort, I have to go through the beginning, find the smallest again. Bubble sort, well, the things will have to bubble down, make their way and bubble down and bubble to the top, so I have to start over for that. So it gets kind of frustrating. Insertion sort, though, just has essentially a virtual queue of items that need to go in, so no worries. No, insertion sort doesn't care. Insertion sort can basically sort data on the fly. So that makes it very useful, especially if you know your data is mostly sorted, then insertion sort is super, super, super efficient, right? If you know that basically that, because it works by essentially pushing it down. Let's go ahead and take a look at my previous example of, let's go ahead and say we've got 3, 2, 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth, right? Or we can actually spin that out more and say 1, 2, 3, and then 8, and then 6 over here, right? So what we'll do is we assume that this is fine. Let's look at the next item. Does adding this item to the sorted section means it remains sorted? Sure. What about this one? Yeah, it's still sorted. What about this one? Yeah, it's still sorted. Still sorted. Still sorted. Adding 7, though, 7 is smaller than 8, so 7 should go before 8. So we're going to swap 7 and 8. Okay. Okay. And what about 7 and 5? Because we're inserting 7. 7 is bigger than 5, so it's fine where it is. Okay. Don't have to check it against anybody else because that stuff is already sorted. Then 6 versus 8. Well, 6 is smaller than 8, so we need to swap that. Then 6 is smaller than 7, so we need to swap those two. And then 6 is bigger than 5, so we can stop. Well, what about inserting 9? 9 is bigger than 10. 9 is bigger than 8, so it's fine. 10 is bigger than 9, so it's fine. 11 is bigger than 10, so it's fine. And then 12 bigger than 11, so it's fine. Right? Basically, you end up basically sorting a bunch of numbers for free when you're doing insertion sort. So it makes it very, very, very efficient. Right? It's got a lot of best case scenarios that come in, and it's really good with a lot of actual real world data, which is actually not always completely random, but generally has some kind of runs of data in it. The other 3 algorithms we learned are these are algorithms that run in n log n time, right? We have Heapsort, which you take O of n time to build a heap, right? You take O of n time to take something, turn it into a heap, and then we proceed to remove every item from the heap, which takes, and we use a max heap in this case. And so each item takes log n time to remove. You're removing n items. It's n log n, right? Hopefully, has everybody had the chance to watch the videos yet? Yeah. For the sorting algorithms. Because I did release them last week to tell you to watch them. And then so merge sort, on the other hand, is that one worked by basically, again, I'm not going to reiterate the video too much, but by splitting things in half. And then basically we split it in half until we get to atomic units, and then we merge those units together. Now merge sort is actually, it's hard to do in place, right? If you're using merge sort on an array list, you actually end up wasting a bunch of space because you're splitting it up into multiple lists, lists into sublists and having to create all those and then merge them together. But linked lists are just fine. Linked lists love merge sort because guess what? We're moving stuff around. We're just moving pointers for nodes, so it's great. So merge sort's pretty easy. Next semester, I fully intend to actually ask the students to write the do merge sort on. They don't know they're going to do it, but they're going to write merge sort on an exam, I think, for in the very first exam when they're doing with the linked list, because it works out pretty well. All right. So, but really, what we want to talk about today is Quicksort. But before I do that, I want to show I want to talk about the last sorting algorithm, the one that's not in the book or in the videos, and that's because all these sorting algorithms we've learned so far are called comparison sorts, meaning they do actual comparisons. We compare items. But believe it or not, you can sort stuff without actually ever having to compare one thing to another, and we're going to learn that using Radix Sort, R-A-D-I-X sort. Now, Radix Sort is actually pretty interesting because of its runtime, which is not O of n squared. It's not this. Nor is it n log n. No. Those are too common for Radix Sort, which is it needs O of capital WN, where W is the word size. Meaning that's so in other words here, where W is basically, if you're sorting numbers, it's the number of digits you have. If you're sorting strings, it's the size of the biggest string that you have. So it's really great if you're sorting one-digit numbers, but because that's now an O of n algorithm. But what actually really makes it interesting is that you don't have to do any comparisons. It's just exchanges. And it uses a queue to do all the sorting. Specifically, it will use, since we're going to be sorting 10-digit numbers, it's going to use 10 queues to sort these things. So I'll go ahead and make a, so I'm going to go ahead and use the line guides as these, right? Where this is where line 1 is the 1 queue, line 2 is the 2 queue, line 3, 4, 5, 6, 7, 8, 9, and then 10 is going to be the 0 queue, and 0 is going to have to come before 1 at the very end. So we'll just have to remember that, okay? So let's go ahead and show you how that works. So these are all the queues, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here's here's the numbers we want to sort with Radix Sort. It's best to show you guys how it works first. It's kind of weird, but once you get the hang of it, it's fine. We're going to sort a bunch of 3-digit numbers. So give me some 3-digit numbers. 111.
184.
184. I'll do 314. What else?
227.
227. What was that one?
123.
123.
400.
400. 321. 957. Right. That should be enough for right now. So here's how Radix Sort works. We're going to do 3 passes. The first pass, we're going to look at the least significant digits of each of these items, okay? And then put them into the appropriate queue. So for 111, we're going to look at the ones place, which is 1. Since it ends with the 1, we're going to put it into the, okay, control. What happened there? Redo is control Y. We're going to go ahead and put it into the 1 queue. So 111 ends with 1, so we put it into the 1 queue. 184 ends with what? 4, so we put it where? 4 queue. 314 ends with 4, so we put it into the 4 queue as well, right? These are queues, so they're going to be first in, first out, right? So the things in the front of the queue, so the things closer to the 4, right? So 227, that goes into the 7. 123 goes into the 3. 400 goes into the 0 queue, or 10 queue, but 0. 321 goes into the 1 queue. And then 957 goes into the 7 queue. All right. So now we put everything into our queues. Now we go through all of our queues from the smallest to the biggest and dequeue them. So we're going to start at the 10 queue because technically it's the 0 queue, right? We're going to start at the 0 queue, dequeue that. Now let's dequeue the numbers from the 1 queue. Oh, and then the 3 queue. Then the 4 queue. And then the 7 queue. Now notice what's a very interesting phenomena that happens over there. If we compare all the least significant digits, they're sorted by least significant digit now. So 400, 111, 321, 123, 184. So now what we do is that we now do this on the tens place. So 400 is still going to go into the tens place, into the 0 queue. 111 is still going to go into the ones queue. But 321 will go into the 2 queue this time. 123 will go into the 2 queue. 184 is going to go into the 4 queue. No, sorry. 184 is going to go to the 8 queue. 314 is going to go into the 1 queue. 227 is going to go into the 2 queue. And 957 is going to go into the 5 queue. And then we do the same thing. We've got we've put all our numbers into the appropriate queues, and now we dequeue. So 400, then take the items from the 1 queue. Then we take the items from the 2 queue. Then we take the item from the 5 queue. 957 from the 5. and then 184 from the 4 queue. And notice now that they are sorted basically if we look at only the second digits. 0, 11, 14, 21, 23, 27, 57, 184. So now the final step is to do it from the most significant digit. So 400 goes into 4, 111 goes into 111, 314 goes into the 3 queue, 321 goes into the 3 queue as well. 123 goes into the 1 queue. 227 goes into the 2 queue. 957 goes into the 7 queue. And 184 goes into the 1 queue. And so if we read, now I don't really have to move them out or anything like that. Oh, this should go into the 9 queue. I don't know why it ended up into the 7 queue. So we look at this. We got 111, 123, 184, 227, 314, 321, 400, and 957. So we didn't have to compare any items at any time and say which one's smaller, which one's bigger when we did this. That's phenomenal. That's interesting. And so with Radix Sort, actually, this is kind of the intent because Radix Sort was developed for for a lot of mechanical machines that weren't able to like do any kind of comparisons, right? Here, like this would sort punch cards and would just do that by you'd take one pass and then you'd go them onto the other, and then you'd throw them onto the top of the machine and have them do another pass. You know, it was a way to basically it's a way that you can sort these with a completely mechanically without having to deal with any like comparisons, which is pretty useful. Now, why does the computer use this? Because first off, the queues do take up space, right? But second off, again, W is the number of bits required to store each key. In other words, how big the thingy is. So for, like, if I'm remember in computers, we're not sorting 10-digit numbers, or sorry, we're not sorting decimal numbers. We're sorting binary numbers. So there's 2 queues, 0 and 1, and there are at least 32, and you need at least 32 passes because they're 0, because, you know, they're 32-bit numbers. So that could take a while. Take 32 n time, which is not too bad, but log n is typically less than 32 most of the time, right? Unless n is like is literally just gotten into the billions. Log n is smaller than 32. So anyway, I just wanted to introduce Radix Sort. So let's talk about the major topic for today and on today's quiz and what. Yes.
So do they all have to have the same word size?
Nope, because what you'll do at that point is pre-pad. So if I had to, for instance, somebody give me 7, I would have done 007, right? And I would just pre-padded and made them all 3-digit numbers in my mind, right? With Quicksort now, Quicksort is a very popular algorithm because even though it's been around for forever, and mainly because of just kind of the elegance of the general algorithm, which is basically move everything that's you grab a pivot, move everything that's smaller to the left, everything that's greater to the right, okay, and then just recursion and do recursion on that. The biggest issue is that whole move everything that's smaller to the left, everything that's greater to the right of the pivot, right? And that's what you'll be tested on the final exam and on today's quiz. So let's go ahead and go over that, right? Suppose you get something like this number, like this list. Let's see, 1, 2, 3, 4, 5. Actually, let me put the 5 here. 6, 7, or 6, 7. Yes. Let's do 6, 7, and then 8, and then 9 over here. All right? So basically, suppose we want to quicksort this. The way Quicksort works is that we select 5 as the pivot. And in the end, what we want is we want everything that's smaller than 5 to be to the left of it, everything that's greater than 5 to be to the right of it, right? If you remember the partition algorithm from the video. Okay, so how do we do that? Well, a common mistake that I see that shows that you don't understand the algorithm is that basically people will go, okay, 5, 6, 7, 2, 8, 1, 4, 3, and then something like that. And that's just not going to work out. Oh, and then 9 over here. Because, you know, how do you get the 5 into the middle like that to begin with, right? How do you know how many items are smaller than 5? How many items do you know that are bigger than 5? I just happen to choose 5 being the perfect middle item, you know, because it worked out that way this time around. So the way partition algorithm works is that we have 2 variables, up and down, and we basically search up. We use up to search for the first item that's bigger, and search down and use down to search for the first item that's smaller. So this is the way partition works. To review, okay, we start at 5, okay, and we start at 5, and we search up from 5. And down from the end. So let's find the first item that's bigger than the pivot. 6 is the first item that's bigger than the pivot, right? Now let's go ahead and search down from the end to find the first item that's smaller than the pivot, which is the first item there. So we found up, the first item that's bigger than the pivot. We found down, the first item that's smaller than the pivot. So we swap them. We put 3 here, and we put 6 there. And then we repeat until up and down cross. Okay? So now we, again, will search up for the first item that's that's bigger than the pivot, which is 7. And now we're going to search down for the first item that's smaller than the pivot, which is 4. Okay? 7 and 4, found them, so we're going to swap them. 4, 7. So we're going to search up for the first item that's bigger than the pivot, down for the first item that's smaller than the pivot, which is going to be the 1, up and down, so we swap them, 1 and 8. Now we search up for the first item that's bigger than the pivot, which is 8 over here. We search down, go down, searching for the first item that's smaller than the pivot. Now notice that up and down have swapped place order, right? Down now comes before up, right? This indicates that we are done. Notice, by the way, what the swapping has accomplished. We've got our pivot, we've got all the items that are smaller than the pivot, and we've got all the items that are greater than the pivot. But what we want is the pivot to be in the middle, right? So the last step is that we swap down in the pivot. So 1 will go here, and 5 will go over here. That's the partition algorithm. And now we're ready to do recursion and do quicksort on this half, and then do quicksort on this half. Questions? So that's the partition algorithm. Doing what I just did right now is guaranteed to be a question on the final. I know because I've written the final. And it's been a question on the final for the past God knows how many years. You know, so that's kind of worthwhile information to know there. As far as other sorting algorithms go, we might ask you to do some analyzing, like not analyzing quicksort, but like the other algorithms, and analyzing, oh, if you modify merge sort like this, how does what's the big O runtime of it now, right? What's the best case, you know, those kind of things. But otherwise, quicksort is the algorithm that we ask you to perform because it's worthwhile knowing how it works. And full disclosure, I didn't know how it worked until I actually had to teach this class. So, you know, all right. So this algorithm was the one that used to be the de facto standard for what you would do, like if you were to sort something, it would probably be using Quicksort. And it was only recently replaced, like being within the last couple decades, by an algorithm called Heapsort. So, and Heapsort is a combination of insertion sort and merge sort in a very special way to make sure that it gets all the benefits of insertion sort and all the benefits of merge sort. All right, so let's go ahead and take a look at the sorting quiz. So the sorting quiz, its password is sort. So good luck with that. SORT, all lowercase.